All right. So what I'm going to do today, I figured we just talk about kind of a simple topic, or not a maybe not a simple one, one that might take a minute to get used to, but it's kind of like the foundation of functional programming. It's recursion. So as opposed to doing looping, we typically build expressions that recurse, and all this means is it's a function that calls itself. So if you've never worked with recursion, maybe that's a good thing. You'll learn exactly what it is today. And then I'm also going to show you a way to kind of like debug your code and like basically just print to the screen everything that's happening without actually relying on the IO monad. So you shouldn't have to change your functions too much to actually to get any of that working. So first thing I'll kind of start out with, I'm just gonna, I've got the code in a separate thing, but I'm gonna write it so that we can see what we're doing here. We're gonna be using the trace function in the Debug.Trace, which is, give me a second. If I go to Haskell.org. So this is a built-in function in the base, or a built-in module in base that allows you to basically inject a bunch of, basically this function has side effects. It's technically not a safe function, but it's in debug, so it's fine. And it basically, it just prints to your standard error. So it'll print to the console. The difference between this and print is that there's no actual need for an IO monad, so you don't, like, this works with pure functions as well. And it also works with lazy functions. So you'll see kind of what that means in this example. But it's just understand it's a little different than print. Print would require you to change pure functions to be impure, whereas this you can just kind of inject a trace. Some little note there. So we're going to start with just a simple, like probably the most basic implementation of a recursive function, which would be a factorial. So we're going to make this polymorphic on anything that's a number. And so if you remember what we talked about with polymorphic type signatures, is that basically all we're doing is we're saying A can be anything, but A is constrained by these three constraints. So A must be showable, it must be a number, and it must be able to have some kind of a quality metric. So this just means we can basically use any kind of number. It doesn't just have to be an integer. I mean, we can make up our own kind of number if we imported the num type class, but for this, we can use the default. So one of the great things about pattern matching for recursion is that it makes it really easy to handle the base case or the exit case. So with a recursive function, anytime you have a recursive function, there's essentially two things you need to think about. There's like the base case and then the looping case, or like, sorry, not the base case, the exit case and the looping case. So like it'll always call itself until something happens where it doesn't call itself, and that's when the function ends. So for example, with a factorial, just to kind of go over what a factorial is again, if I want the factorial of 5, then this means 5 times 4 times 3 times 2 times 1. If I want the factorial of 7, right, then it's going to just be 7 times times 6 times 5 times 4 times 3 times 2 times 1, right? So that's what we're doing here. And all we're doing is giving it the first number, and then it's going to recurse. It's going to recursively multiply the values until it reaches 0. So when it equals, so the first case that we need to think about is when our n becomes 0, in a factorial, we multiply by 1. This is just because if you multiply by 0, it'll be 0. But this right here is our exit case. So as soon as, like, we're going to recurse until n is equal to 0, and then we're not going to recurse again. And you'll see that in the next example here. Otherwise, so this is a guard in Haskell. This is a way of pattern matching on conditions. So you can pattern match on functions themselves, but you can also pattern match on conditions using this pipe operator, and that's called guard syntax. All of this, by the way, too, is in our learning materials, but that, just giving you kind of a rundown right now. So for a factorial, in the otherwise case, what we do is we take n. So n comes in first as 7. Then we're going to multiply it by factorial of n minus 1. And that's it. That's a recursive function. So what we're doing is we're actually calling this function again with some change. So, you know, in a for loop, you might go like, you know, for int I equals 0, I less than 7, I plus plus. And I've never actually done this in a for loop, I don't think. But you could if you had some kind of variable up here. Right, and you just kind of went, you'd have to start out with 7. And then fact, it's actually harder to do this without recursion. You just say fact times equals I, and you would go minus minus. So it'd be something like this to get a factorial. I'm not even going to test this. It's a lot easier to do it with recursion. I'm realizing every time I've implemented factorial, it's been recursion. But that's essentially effectively what this is doing, is each time it goes through the loop, it's changing that I. So this here becomes our, like, basically if we were to just pass in n each time, this function would never end, right? Because we're never going to hit this base case, or we're never going to hit this exit case. So by subtracting 1 from this each time, first of all, that's the implementation of a factorial. Second of all, that actually brings us closer and closer to this exit case with every iteration. So that's kind of the difference between recursion and looping, is that rather than like having a while loop or a for loop, we're actually just calling the function itself. There's a couple reasons why it's more powerful and safer to use. For one, you say you write this function, at any point, someone can come in and call some other function here, which may or may not change the value of fact. So this kind of gets into the whole idea of like mutability versus immutability. In Haskell, remember, we do everything in immutable fashion. So in order to loop immutably, we need to use a for loop, or we need to use recursion. There's other benefits as well, but that's kind of one of the main ones, is that it keeps our entire loop pure and treats it as one expression. It's very difficult to, like, without, you could come in here and add a new base case, but it wouldn't affect this case, and you would know about the failure right away, as opposed to, like, maybe this function has some side effect, maybe this function works today, right? But then in, say, a month, someone comes in and adds a different function in here, which now breaks it, right? And so the whole concept is to keep all of our logic pure and to keep it local to the function itself, not to use any kind of global state or immutability, or mutability. We just focus on using immutability. So
I'll add too. Actually, I was inspecting your function, and fair enough, because like, of course, like, fair enough to have a mistake in this context, because like for the object oriented side, um, I noticed that you had I equals 1 to start, whereas you would actually want I to equal the same as the factorial. Like if it's like factorial 7, I should also be 7. Otherwise, it'll exit after
yeah,
1.
exactly, right. Like I mean, I just was doing that quickly, but those kinds of things, like, you're not guaranteed to. And to be fair, that is something that I would have found out, like, as soon as I ran the function. It wouldn't have given me a factorial, but it's more because there's, like, errors that you get right away are fine too. Like, we want to try to move everything to the compiler, but like, sometimes there's just an error in the logic that you write, right? Like you're just not writing the correct function. And that's okay too, because you'll know as soon as you run the function. What we want to avoid is scenarios where things work now and they don't work later, or there's a missing edge case that you didn't think about. These are the problems that we try to avoid, because, like, unless you're like a perfect programmer, like, you're always going to make logic mistakes, but you want the logic mistakes to be known right away.
And also too, like, even the point that I was making was not to bash what Kyle's doing. Oh, like, you didn't write your function properly on the first try. Like, what is that? But that also, like, indexes provide another area of like logic you have to reason about. So it's another area you can get wrong depending on the case.
Yeah, like, I would argue this is so much easier to reason about, especially for something like a factorial, because it's the actual logic that you're doing, whereas for loops they kind of abstract away the actual math behind what you're doing, and that can be nice for, like, simple cases, but more often than not, like, how many how many people have ever seen a list out of index error at runtime? I know I get them, like, every couple weeks at work, right? Um, and it, like an actual system crash because a list was out of index. It's like, that should never happen. Um, it won't happen with recursion. It's kind of a way to look at that, if you're recursing over the types appropriately. So here we go. I'm going to just run this just to show that it works. Oh, I need a main function. I'm not even going to use it right now, so I'll just say, okay. So if I want the factorial of 5, we get 120. If I want the factorial of 7, we get 5040. So this is correct. But how do we know? Like, I mean, we could look up online. We could say factorial 7. What is factorial 7? Oh, it's 5040. Okay, I guess we're doing it right. Or, you know, it gets even harder if we say factorial of 123. Like, that's a big number. So what we can do is we can actually look at and inspect what this function is doing at every iteration. And this actually kind of helps us like understand what's happening too. Because like sometimes when you're writing Haskell for the first time, you might not understand exactly how this like executes, right? Because you might be used to imperative where it's like, I'm going to run this instruction, then I'm going to run this instruction, then I'm going to run this instruction. But with functional programming, it's a little bit different. So what I'm going to do is I'm just going to add the trace function to this function. And typically what I'll do for that is I'll just copy, because this is really just for debugging. So I'll just copy the function, add a little backtick at the single quote here, call it factorial prime. And this is where I'll add my debugging statements. So I can do, and you'll notice I can just write trace, then I can add the log of what I want to say. So I'm going to say factorial 0 equals 1 here, because that's just standard. And then you just put the logic that you want to run after. So trace basically just takes a string and a function, and then it just runs it prints the string to the screen every time the function is hit. And so what I'll do for this one now is I will actually just change it up a bit. I'm going to copy this for time's sake. It is, rather than doing this here, I'm going to put it into a result. Give me a second here. So this is just the same thing. We're just assigning a tag to it so that we don't do it twice, because we still want this to only occur once, but we want to print it, and then we also want to do it. So all I'm doing here, I'll just do it like this even, so it's easier to see. Plus equals plus show result, and then we're just running result. So all this is doing, this is basically the equivalent of just doing like a console log in your code. This plus plus is just appending strings together. So like quite literally, I'm just appending these strings together. I believe there's short forms for this, but it doesn't matter. Like in how other languages, you might go like backtick and then $, it's a curly brace, and you can put it right into the string. There are extensions for that, but right now, we're just doing it this way. So we're saying factorial, we're going to show n. So we're basically saying factorial n equals n times factorial n minus 1 equals show result. So for each iteration through this, we're going to see the intermediate results. So if I say factorial prime of 5, that didn't work. Wait, what? What did I do wrong? The demo gods are not with me today.
Oh, are you? Oh, never mind.
Oh, no, that's why. The recursive iteration was calling my initial factorial function, which doesn't have tracing. So that'll do it. So if I run factorial prime 5, there we go. So now we see each step through the function of what it's doing here. So factorial 0 equals 1, that gives us 1. Factorial 1 equals 1 times factorial 0 equals 1. Factorial 2 equals 2 times factorial 1 equals 2. So we're seeing here now that we are in fact calculating the factorial, because we can say 24 times 4 and 24, right? Or sorry, 5 times 24 is 120. So yeah, great. We now have debugged our factorial function. Maybe it helped us actually understand what it's doing under the hood. And we've actually been able to print each iteration. Now, I'm just curious about something. Let me try something. I did this on a different function, but I'm going to see if it works here as well, so I can show something a little cool. Okay, no. So we're going to talk about that later. Because this function is strict. So it requires you actually to run every single factorial until it gets to the 0 case. Ignore that for now. So
yeah, and by default, everything in Haskell is lazy, just simply meaning that like it doesn't evaluate until it has to. So like let's say you like called factorial somewhere, but you like never printed it to the string, or sorry, never printed it to the screen. Then it would never actually evaluate that expression. It would just build the expression and how to calculate it for later, but never actually run that.
which is awesome, and so one thing I'll say on that is other languages do have some form of laziness. Like you can pretty much, like you can do it's just not as easy. Like you can do lazy computation in say Python, but oftentimes when you can have lazy computation in Python by just having a factorial function and not calling it until it's like inside of an if statement. But one of the benefits about laziness in Haskell, it's actually at the compiler level, and there's a lot of tools built in that actually help, like when it optimizes, because like every compiler actually has like an optimization phase. So like the code that we're running here is not the code that the compiler actually runs, right? The compiler is going to compile this down into something that it understands, and then it's going to go through an optimization step, and it's going to be like, which of these functions do I not even need to call? What cases am I never going to call, etc. The Haskell compiler actually goes one step further with a concept called memoization. So, and that's memoization. It's kind of funny. It's kind of like memorization, but it's memoization. I wonder if that's a joke. So what this means is that it's actually caching intermediate results. So each of your, and I'll show this in this example, it kind of just happened by accident. And I was like, why is that? Oh, memoization. So it'll actually cache, not only is it going to only run lazy expression, not is it going to only run the expression when it needs to, it's only going to run the intermediate expression. So like each iteration through that expression, it will only run if it needs to, if it hasn't run it in the past. So say we have a function that calculates the value of 1700 is 45,000. Next time you call that function, if it sees a 1700, it will just automatically put in 45,000. Doesn't have to do the calculation again. And this is something that it can do because it's pure. If our functions were impure, the compiler would not be able to do that. And so most languages can't actually do that. This is insane for performance benefits, because say you have like an array of 1 million values, right? Maybe only 1,000 of those million values have changed, but in most languages, you'd have to calculate all million values again, Whereas in Haskell, it's like, no, this hasn't changed. This value will always produce this value. So we're just going to print it out to, or we're just going to give it to you. Here it is. And so there's actually like a cache inside of Haskell that that will do that, and that's insane for performance benefits for data, any kind of data analysis stuff. Haskell has been shown to have much higher performance speed, especially when you get into areas with like large amounts of data, because it has that. It's able to enforce purity in your code, and because of that, you get a ton of benefits. And that's just one of them. So I'll show you that in a minute, but we'll kind of just move on with some of this recursion stuff. So if I say I'm going to create another function that just sums a list. So we'll say sum list show a num a, and we don't even need to, whatever. We'll constrain it for numbers for now. Oh wait, sum list. Yeah, we would need to. I guess we could sum characters, but that wouldn't make a ton of sense. So basically, for this, what we're going to say is when we have an empty array. So what we're doing is we're taking a list of A and we're returning an A. So when the list is empty, we're going to return 0. That's our exit case. We always put our exit case before any other case, because the way that this pattern matching works is it runs the functions, or it matches from top to bottom. So every time it comes through some list, it's going to come here. It's going to say, did we match this pattern? No. And then we're going to move on to the next one. Another thing to note here, since I've got language server working now, you can actually see while I'm writing this, it's saying that the pattern matches are non-exhaustive, right? So it's saying, hey, you forgot about the case where there is something in the list. And this is really powerful because it's actually telling you when an edge case is missed. And the better you are with your type system, the better this pattern matching will be at telling you, hey, you missed something. So we can implement, and if I just do this, then you'll see that error goes away. Although, what's it saying about A? It's just telling me it's not used. So yeah, so basically it's saying you only handled the case where there's an empty list. You need to handle the other case. And what we're going to do is we're going to deconstruct this list using the cons operator. So this is called a string comprehension or a list comprehension in Haskell. Python also has this concept of a list comprehension. And basically what this is going to do, if I just take a step back for a second, basically a list in Haskell, like you can look at it this way, or the way that Haskell is actually creating this value, because if you remember, everything in Haskell is just a function that returns one more function. Everything is curried in Haskell, so that means there's only ever a function with one input and one output. We just string them together in order to create a function with multiple inputs and a single output. So what this really is 1 cons 2 cons 3 cons empty list. So this is how Haskell actually represents. Sorry, I keep pressing the wrong button. This is how Haskell actually represents a list. Is with this operator, the colon. So anything colon something else is essentially, it'll concatenate two lists together. And so what this is doing is it's creating a list 1, list 2, list 3, and then concatenating that with the empty list, and it's creating our list for us. So these two are equivalent.
So Kyle, just I think a good example too would be like, so let's say some list we wanted to match on specifically for whatever reason, just to get into pattern matching here, we want to pattern match on a list that has exactly 3 elements, like you've shown here. Does this some list XXS do that, or Yeah.
You could do that. I don't know.
And then
I've
the
never
empty
done that.
list. And then the empty list.
Oh yeah, then you would need
You've done it. Yeah.
But the empty list would be handled by this case. So
Well, or yeah, no, sorry, I'm maybe I'm getting sidetracked here. I was just saying like, what is the like, trying to illustrate like more about what we're doing with that pattern matching.
yeah. So I'll get to that next
Okay.
here. So basically, with this XXS, what we're doing is we are deconstructing or what would it be called? I guess unbinding the types. So without getting too like theoretical, like for now, just understand that like this is how you do it. But if you want to like get right into the theory, like you can, for example, like you can, so say we had a type that we were passing into some list and we weren't doing a polymorphic function. We did some like, we'll just say it's a list of tuples. So it's a list of string, and then we return a string, right? Basically, this would be like, we go through it, we concatenate these both together, and then we concatenate those together. So it's like we're combining all of these. We can, or you know what, to make this simpler, I'm not even going to use a list. This is just going to be concat, right? Concat. There's two ways we can do this. We can say, I want to concat, we'll take S, we'll call it S tuple, so a tuple of strings. Then we can take the first of stoop, we concatenate that with the second of stoop, and that would work. But what we can also do is deconstruct that in the type or in the pattern match itself. So we can basically say I want S1 and S2, and we're going to say S1 plus S2. These are both the same. Both this and this are the exact same. And so what this is kind of saying is that like you can actually deconstruct types inside of the pattern, inside of the type constructor, or sorry, inside of the function definition, inside of the pattern matching. So here we're just doing the exact same thing, but instead, and you can see this is actually going to come full circle perfectly, is that a tuple is just represented by the comma function. Like all of the, like this is a function, it's not an operator. This is a function, not an operator. Comma is a function, not an operator. So I'm gonna. This is, I think, a good tangent to go on.
I like.
And we're gonna look up.
I like the use of tuple for this example too.
Pardon?
I love the use of tuple for this example.
Yeah.
So.
Tuple is just a data type, and it has a function. Where is the function? It has a constructor, comma, and this gets into prefix versus infix. If you remember, I think we talked about this a little bit before, but we haven't really gone deep on it. Like you can create a tuple, and for example, a tuple you can create in two ways. You can say, I want to use this operator as a prefix operator and have that on some string and some other string, right? And this will give us this representation, right? So this is these two are equal. We'll say equal. Or we can just do some string some other string. These both equal the exact same thing. This one is prefixed. This one is infixed. So I believe we talked about this a little bit in the tutorial. If not, I might add this because it's something that can be learned like rather quickly, but it's a good thing to note because sometimes you'll see things used in a prefix fashion. Sometimes you'll see things used in an infix fashion. They're the exact same thing. It's just you can, like, this comma operator will take an A and another A and give you another A, or like a tuple, like, I guess it would give you a tuple. I don't know the exact thing, but it's effectively what it's doing. And so will this when we do it this way. So, or I guess it technically like that, something like that. Both of these just without beating this with a stick, both of these functions do exactly the same thing. It's just we can use an operator in this fashion, or we can use it in this fashion where it's in between two arguments. And that can actually be used with any function. So any function we can. So for example, say we have our concat function. We can say, I want to concat this tuple. Right? Or I can write these are both exactly the same. What does it say in there? If work declaration. Oh, it's because concat already. Oh, what is it? Oh, it's because this isn't a function. I'll say my val equals. And just to kind of drive this home, what am I doing wrong? Ambiguous incurrence concat. Oh yeah, okay, that's where, because concat already exists. So we'll just do concat prime just to put this example across. So why is that? Oh, okay, no, that's not going to work because here, if I just admit, so separate example. That's because I would need to like turn that into a tuple. But let's just kind of do this one, concat. This sorry if that was confusing, but I'm kind of just showing a separate example now. So these two are the same. My val and my val2 are the same. So if I print out my val, some string, some other string, my val2, some string, some other string. So it's just to show that any function can be infixed by putting the backticks around it. So there's just two terms, prefix, infixed, and it just determines of whether the function goes before two arguments or in between two arguments. And the left will be S1, the right will be S2. So it's kind of a nifty feature. You might see that, you might not. But yeah, so in the long and short of it, that's why we're able to deconstruct this list using the cons operator or the cons function. Does that make sense? If it doesn't make sense, put a question in the and we'll get to that for sure.
And the reason ultimately for that is you know, like the if we look at like the data declaration of like a list, this is all the theory there is really to it. Is like if you look at the data definition of a list, you see that there's two options. There's either the empty list or a value tacked on to some list. And that like the data declaration itself, I don't think we'll show it here because it can get a little confusing. But ultimately, it is itself doing recursion. It's a recursive data structure that has two options. It's either an empty list or a list of stuff. So
Yeah, there's so many. I'm not going to get into it right now.
yeah, you won't find it either. I don't
That'll
know.
be your homework. Go look at the list type and see if you can understand that. Okay, so for this, very straightforward. We're just going to again say. So now, basically, what this gives us is this gives us an element from the list, and then the rest of the list. So we're basically just peeling off one value at a time this way. So we'll say we're just going to return here x plus sum list xs. And that's our sum list function. So we got sum list 1, 2, 3 gives us 6. And again, just to drive this point home, we could also say 1, 2, 3 gives us 6 as well. Okay. So I will do again my sum list prime. And for this, sorry. I'm going to say trace sum list. Oh shit, what am I doing? And then here I'll just do it. Okay. All right. So now we can see everything that it's doing. First time through, it's got 1, 2, 3. Second time through, it's just got 2, 3 in the list. Third time through, it's just got the 3. And the last time, it's got the empty array, which hits this base case, returns a 0, and then it doesn't recurse again, right? So our value is left with x equals 0 plus 1 plus 2 plus 3.
I'll also point out some intuition here that if you look at, where Kyle, you're using the dollar sign, sum list $, 1 colon, 2 colon, 3 colon, right before you reloaded, and you'll notice that like the sum list is consuming from left to right. I don't know how to highlight it. Like the second last or the third last entry for GHCI.
Sorry, which one are you saying?
The sum list right before you recompiled.
Here?
That so you'll see that like when we're building a list, it's like 1, then 2, then 3 in order, and like that we're consuming from left to right when we recurse here. Like
Yes.
we wouldn't pull out 3 first. We would pull out 1 first, and then 2, and then 3, because that's how we built the list. So it's like in a way it is a stack.
Yes, and to Nick's question, Stack Overflows are still possible. They're less likely because of laziness, but obviously you're still working with a computer, you're still working with stack memory.
I've only had them ever when I like had a non-obvious bug. Like there's a couple times through like Reflex where I have gotten into some very complicated logic, and then like it results in a stack overflow. But like
Yeah,
I
so if it basically if it can like it avoids stack overflows for pretty much like unless you're doing something weird like Galen said, you're going to avoid stack overflows because it doesn't just, to my understanding, it doesn't just put everything on the stack and then wait till the end. Like it actually, here,
well, it's because of the laziness too, right? Like I mean,
let's try it. I don't use that one because
and
it's gonna print.
yeah.
Oh gosh, what did I do?
Oh, well, and also
All
too,
right, this is
like
gonna take a minute.
because of the laziness, like all it's working through, um, implicitly through the REPL. When you say like when you like so like how Kyle typed in my val, the what that actually under the hood means is like print my val. We just don't have to write print, right? So in the REPL we could say my val or we could say print my val, and it'll be the exact same thing. Um, and as it's going through each individual like print or put line or put string line, or even I guess put string would be what's used here, because we're not going to a new line. It's just evaluating what to print next. And so like at each and every single point in time, it's saying, oh, I should print 55,001. Oh, I should and then evaluating the next piece, performing that recursion. So like, right, and that goes back to the lazy evaluation. So we never have this massive stack to run through, because it's just
Yeah,
evaluating as it goes.
there's ways to avoid it. Admittedly, I'm just asking ChatGPT right now, and it really comes down to like left versus right evaluate. Like,
Well, I think even the point
you will get stack overflows. Like because like for example, with a function like this, because you're summing together the list, I'm pretty sure this just builds up like a long chain of like 6 plus 5 plus 4 plus 3 plus 2 plus 1. And then at the very end, it sums it all together. Now, there are probably ways to optimize that further. I'll say there are definitely ways where it's like, why does all this need to be on the stack? Why can't I just do like 6? My computer is just freezing because I just did a sum of a million numbers with a Debug.Trace, so I apologize. I might just can't like close out of Emacs, to be honest.
I'm also thinking further too, and like I think simply like where it comes from is like if you have a Stack Overflow is just when you force strict evaluation, um, like
Yeah.
so yeah, you would force it to evaluate a million before printing anything, and that will
Not even before printing, but before accumulating. Like if you have an accumulator value, you won't run into the Stack Overflow issue, which like this question's kind of messing me up because I always thought that it just accumulates during computation, but it really depends on the function that you're actually writing. We'll leave it at this. It is possible to have a Stack Overflow in or in Haskell, but there will always be a way to solve it, if that makes sense.
Yeah.
There'll always be a way to further optimize your code so that you don't run into that Stack Overflow. Because Stack Overflows are it's like the one thing that can happen with a recursive function is that you're building up a massive, like, because each function call is a call on the stack, right? So every time you call a function, it pops all this information onto the stack. Depending on the size of your stack in bytes, you'll either overflow or you won't. But I'll just say I've never run into it. Maybe I'm not working with big enough data.
But
But
it wouldn't even matter, like, even if like you did like, like sum through infinite, like, a million or whatever. I mean, perhaps you could pick a big enough number, but like, how often are you actually picking, like, show me the sum of like 1 through a million, or no, sorry, not even like 1 billion, 1 trillion. Like, you'd have to really be looking for it. You'd have to be trying to get a Stack Overflow.
I'll do this one. Oh shit, oops. Go. That one should happen a bit quicker. Like, that was fast. Let's see if we can get a Stack Overflow. This could take a little bit longer. Yeah, right. So it can't sum 10 million values because it gets a Stack Overflow. But there is a way to do this, and we'll look into it for the next example. But good thing to note. Okay. And I think where you could make this better is probably using folding as opposed to just kind of the way that we're doing this. Like, there are functions created in Haskell specifically to handle these kinds of scenarios. But what we're doing right now is like a very rudimentary, just like take X, add it to the next function, right? Okay. I'll do one more example here. Get some time for questions. I'm going to implement quicksort. Yay! The sorting function that is anything but quick, but it's fun. Quick implementation, not quick on your hardware. This is also a very commonly asked interview question, is how to implement quicksort. So I figured it was relevant here. So what we're going to do here, this might look a little weird at first, but we will get into it. We're going to call quicksort function again, but we're going to filter out all the values that are less than or equal. And you can see here how we're using this as we're using this operator as a prefix function, as it's actually a partially applied prefix function. So this is where we kind of, what we were talking about before here, it also mixes with a concept of partial application, where we can pass in one value to this prefix function, and now this will be a function that's still awaiting, so if we have less than or equal to, takes an A, and returns, I believe it returns a bool, what we've just done here is we've gotten less than or equal to a bool. So we've partially applied this first argument to the function. And so now it's just going to be looking at, this is a function that checks, that returns bool if anything is less than or equal to x. So, you'll see this a lot in Haskell. And at first, you might get a little, like this is one of those areas that you kind of have to, once you get wrap your head around it, it makes a lot of sense. But it might seem a little weird at first, and that's okay. You really just have to think about like, how many arguments are there to this function? So this function requires 2 arguments, and we've already given it 1 argument. So there's 1 argument that hasn't been given to it yet. And so it's partially applied. This is still a function. And this is actually really powerful. You can't do this in other languages. Well, you can if you have like certain libraries. But yeah, Haskell makes this really easy. It's built in and it optimizes it and everything. So we're going to do that. Then we're going to append it to list of x. And then we're going to call quick sort again with a filter of everything that's greater than x. So this here is our quick sort function. And we'll just keep that on one line. That's fine. Sometimes I like to put it on multiple lines, but I think this is easy enough to understand. So I'll show it working first, and then we can, because this I find is where like debugging it actually helps, because you can see what it's doing under the hood. So I will quick sort, and if you notice, this just, it's polymorphic, so it can take anything. It can take anything that has ORed, which means basically anything that can be ordered, anything that's a list. So it could be a list of numbers. Oh, don't do that to me. What did I do wrong? What? Demo gods, please help me. I swear this worked last night. Give me a second.
Sorry, I'm feeling a little under the weather. I'll admit. Had to step away for a second.
All good. So it's that time of year.
Yes. Haskell will me. No more laziness for me. You know.
Okay. Might be something that I changed with that function. Bad, Kyle. Never change functions. I know this one works. Yes, Nick, great point. Yeah, so fold, and that's what I was getting into, fold right. If you were to try fold left, that would probably fail. I urge you to try that. Fold L. And that really comes down to how the stack works, right? If you're folding from the right, you're always getting rid of values. You're decumulating. Whereas if you fold from the left, you're going to just accumulate values. I'm very curious if that works, but here, let me see. Works still? Okay. So yeah, fold has built-in logic to avoid Stack Overflows, as far as I'm aware.
It's just because it would evaluate before trying to build into a massive expression.
Yeah. It's gonna, fold evaluates after every iteration, right? So it's as opposed to, so if you're like, recursion's great, but if you're trying to work with a value of 10 million, use a fold. Or like a list of like 10 million values, use a fold, right? You can pretty much use folds for you can use folds where recursion is used, like I'd say probably 100% of the time. Just sometimes recursion's easier. And if you know, I folding on an unbounded, or sorry, recursing on an unbounded list is technically dangerous. As you can see there, if the list keeps growing and growing and growing, like if you're recursing over just like standard recursion over a list that you get from a database, like say it's like a list of messages in a database, as soon as that list hits 10 million or like some value that's larger than the cache on your server, you're going to get a runtime exception. So you notice this here, this was a runtime exception. We don't want that in Haskell, but there's kind of no way to avoid that when you're specifically telling it to do that. So that's why folds are better for that kind of thing. Okay, don't fail me now. There. It's got to be something with the way that I was chaining these functions together. We're not going to worry about it right now. So if I have the filter here, oh, that's why. No, I found it. And I want to use the simpler solution for now. This is supposed to be greater. Huh, that was a typo. Yeah, okay. So this function does work. I was like, there's no way that just moving it into let statements fixes it. So
it does help to think it through, of course, but
yeah, it does help to think it through. But yeah, so okay. So what we've done here, and it'll make more sense when I throw the debug traces in here, and maybe you use the debug traces to help you actually write this function, right? What we're doing, again, we're taking off X from the rest of the list. So we start with a list of 1, 4, 2, 3. We pass, basically we're calling quicksort function twice for every, for the left side and the right side. So quicksort, way it works is it basically looks at, okay, is this new value less than or greater than the current value? If it's less than, put it on this side. If it's greater than, put it on this side. And it just does that until the list is sorted. It's not the most efficient type of sort, but it's an easy, quick implementation of a sort. And so what this is doing here, filter is returning us a list where X is less than or equal to, basically it's giving us everything from XS where X is less than or equal, where it's less than or equal to X. And then here, same thing, greater than X. So just, I'm gonna implement the trace for this just to help me explain it, because it's a little nuanced. So all I've done is just broken these into functions so that they can be, or values are functions, so that I can like print it twice and I'm not recursing twice. Because if we call this inside the trace as well as here, then it's gonna run it twice and that technically breaks So it's good practice to set variables as well. If I do this and use my traced quicksort, then we can see exactly what it does. And this, you might be like, whoa, I wasn't expecting that. So what it's doing here is each time it hits an empty array, it's going to print this out. And so you'll notice here we're calling quicksort twice for less and greater. So first time it goes through the list, and I hope I don't butcher this explanation. First time I go through the list, we pop off the 1, and we're left with 4, 2, 3. So that's what the first time that we do this. Then we're going to check, okay, is there anything else in the list that's less than 1? No. So quicksort less gets the empty array filter, and then that hits this base case, and it exits. So it exited there. Then, and it's actually building up the accumulation, so it's a little confusing. 1 second. 4, 2, 3 equals 2, 3, 4, 1, 4, 2, 1, 2, 3, 4. Okay. Admittedly, I could make this a lot easier to understand because like it's not telling me whether it's in the greater than or the lesser than. So effectively, then it goes to the 4. It says, is there anything less than 4? Yes, 2 and 3, which is here. It's kind of all out of whack. You would expect it maybe to be here, but no, that's because it's evaluating it basically. Okay, yes. So it evaluates all the exit conditions first because they don't require another like every time that it hits here, it's like it's finished, right? So all of these exit conditions are occurring before the next quicksort actually happens. And if you notice, this is kind of backwards, like, and that's just because of the way that recursion, it builds up and then it's like an accordion. Like you're building up and then we're putting them back in place. So now we start with, we add the 3, then we go 2, 3, and then 2, 3, 4, and then 1, 2, 3, 4. Okay. And these cases are just all the times that it was either lesser than or greater than was empty. And yeah, it's a little confusing just because of the way I'm printing it. I'm wondering. Yeah, I'm not going to worry about that right now. But basically, this shows us how the recursion is actually happening. And so under the hood, it might be a little weird, but getting used to this kind of thinking is important. Admittedly, you don't have to think too much about how the stack handles it. Because like here, like for example, even like for here, I'm just thinking like we're going to run quicksort on a filtered list of lesser than, append that before the value, and then also append anything that's higher. So each time we come through quicksort, XS is going to be a slightly more filtered list of whether it's less than or greater than. And that gives us our quicksort. Galen, I don't know if you want to add anything there.
No, I think that's okay. Yeah, I mean, No, I think that's okay. I think it'd be probably better to just see what questions people have, and then we can go from
Yeah.
there.
So one more thing I wanted to showcase was this idea of memoization. So one thing to note is that this can also be done with any list, and a string is also a list. So here we go. I can pass in this, and we get A, B, C, D, E, F, right? Similar kind of concept where you can see it's going through and reconstructing this list
And
back into the,
I guess the one thing I will add at this point actually is I forgot that um we were using um or like that I forgot how you had defined your function. So um the reason we can use quicksort for both numbers and letters here is because we're not like that might be confusing because like we couldn't use of course letters for the previous case where we did some list.
yeah,
Um,
it's because we had num here.
right. And so ord just simply has a instance of ordering. So like in other languages you might convert a character to its ASCII value, and that's one way you can like sort things, but implicitly that's just handled through the ord instance for character. So that's why
Yeah,
we're
and
able
that's
to
a
sort it.
good thing to note is that it's actually very relevant. For example, if I were to change this b to a lowercase b, it's going to put it at the end. And that's because these are just it's just looking at the ASCII values uh, of these characters, right? So b, lowercase b comes after uppercase letters. Like all of the uppercase letters are first, and then all the lowercase letters. If you look at the ASCII table, to anyone who isn't aware, look up ASCII, ASCII.
Yeah,
This is a good thing to know, so I'll just show you what it is.
totally.
Oh, not responding on a new tab?
I
Come
mean,
on.
ultimately, ASCII is just the like how characters are represented to a computer in the most basic
Yeah,
sense. Like
yeah.
there is systems that build or that are more extensive than ASCII, like UTF-8, which allow for
Unicode, yeah.
more characters. Yeah, um, but
But anyways, yeah, my computer's freaking out on that for some reason. So what I will do is one more example here just to show, to bring everything together. So I'm going to let my val equal quicksort. So this is where laziness and memoization are really cool. We're going to say my val. So now I have this actually defined with a label in my code. If I call it the first time, you can see it's running through the quicksort code. If I call it a second time, it does not. So this is because when it tried to run my val, notice like I didn't reassign anything to my val. It's not like I like when I say this my val equals quicksort A B C D E F, this is not evaluating quicksort. This is just assigning the label to this function. So by calling it the first time, it actually evaluates the function. And then by calling it the second time, all of these values that it came from the cache. So this is a very simple example of laziness and memoization, but like this is actually very powerful. Like if you were to look at this in the context of Python, it might not seem like, it might look like we're just like setting the value to my val and then printing the value, but no. You know what? I should not call it my val. My func. So this is a function. This is not a value. This is a function in our code. So if I run my func the first time, it executes it. If I run it the second time, it's pulling all of those values from cache because it's pure. So that's extremely powerful for performance benefits. You know, if there was something in this list that changed and it still knew how to handle A, B, C, when does it not happen? Great question. So if I try, they're not quick sort. We'll do.
Well, what if you re-entered let my func equal quicksort prime ADC ABD CFE? Like, what if you re-entered that line? Would that reset it?
Can I do that though? Because it's maybe,
Well,
but
it
it
might
would not be that I've already defined the function.
it might delete that like entry is what I'm thinking.
You can reload, and that'll do that. Well, I'll try that after. Just give me a second.
I
Yeah.
mean, and if we think about this another way, assuming that everyone is familiar with maps, you know, like we can think of this as like Haskell being a map where you know the key is some string, some you know some name or whatever, and the value is some expression or result. This is how I at least imagine that it's running it in the background. Is that we're just adding, like we first say let my func equal quicksort prime, you know, our list, and my func has a definite value at that point, right? So at that point we add to our map an entry for the name of my func, and then its value is some expression that um, we haven't yet compiled. You know, but then Kyle calls my func that forces the value at that key to evaluate, and then from then on we just keep that key, right? We just keep the key in the map, and so like it'd be very easy for us to like ourselves implement some like idea of memorization, because like a lot of like the difficulty is already handled by having um, immutable immutable names, right? So like as soon as a name is picked for the lifetime of the program, that name only has one meaning, right? Even if we had like whatever the name is, like you know, let's say like x1, x2, x3, and you know, and let's say like that xn, um, okay, and they continue to build off each other. Like each individual point, or for the lifetime of the program, or for each individual variable for the lifetime of the program, they will have the same value, as it originally was set to. Um, so even if like in the REPL, if we were to like, because we can be a little bit more free with the REPL, if we were to say my func2 again, or let my func2 equal something, um, this isn't the same. We could not do that in the actual program, right? Like we can't say let x equal 1, let x equal 2. We just can't do that, because as soon as x is given a value, it has that value forever. And so that's why it's very easy and trivial to do memoization and keeping that value in cache.
Yeah, so it has to do with the fact that we're forcing this, like this function is strict by nature.
I think you're.
Um,
I notice you're also calling.
'Cause you can't lazily evaluate addition, which I'm realizing is, yeah, you broke my brain on this one.
Sorry,
I need to.
I noticed you're using sumless prime, not double prime, on line 58.
Thank you, sir. Give me a second. Yeah, no. So it has to do with the fact that this function isn't lazy. Let me get back to you on this. There should be a way to make this memoize as well.
Wait, so hold up. This worked for what? It
For
was
quicksort,
quick sort.
but not for sum list.
I'm not sure off the top of my head why that would be the case. I mean, it would just um yeah.
And I'm pretty sure, yeah, like Nick said, I'm pretty sure it has to do with the plus not being lazy.
It could also
I know that this is strict evaluating.
well
Um,
no, sorry, the plus is lazy, but like it could
plus
just
plus is
it could just like sorry, it could simply be because of the REPL. Like let's say sorry, like if you said okay, so in some list the val of 59 in like let's say you have um like in your in statement on line 60 you use the val twice, it's only going to compute it once.
yes, yes,
I think this is I'm pretty sure this like plus is lazy. The plus sign is lazy. It's more likely because of the REPL. I mean, there is like certainly a way that you can ensure that even in the REPL, it shares that memwise value. Um, but I know for sure that if you were using this in the context of a normal program, because the REPL is a bit of an abstraction, right? Like it's
yeah,
but yeah, if let's say right, so the key thing is like let's say we used the sum twice. That will only compute the sum once.
yeah. No, well, okay,
When
yes,
you're
it'll.
calling sum list multiple times. I
Hmm?
sorry. You're calling sum list prime double prime multiple times. So it's hard to tell from the trace whether or not the sum is what's evaluating. Like you could do you could create two sums from like 1 to 8 or whatever. Like create like if you have let's say line 62, you say something like um, sum1 equals sum of 1 to 10, and then you like pick a different sum, and then you add traces to those. Um, it might be a more clear way to see like how many times it's evaluating. Or actually even sorry, if you were to do someone like sorry, I was just going to use just the normal sum function to illustrate this, and then just add some let's say sum2 equals sum1 plus sum1, and then like add traces in, we might be able to see
Hmm.
its result. So we're either expecting it to evaluate twice, and meaning it's not memoized or cached, or evaluates once.
Yeah,
So right, so we're seeing that it's using sum1 twice, but it only has to compute. It's smart enough to know that given based on the fact that Haskell is immutable, this value, the name of sum1 will always be the same throughout the entire program, and we never need to worry about it changing. So if that's the case, and let's say we're building the language ourselves, why would we recompute the value, right? If we can do less work, we can like compute it once and then just use it a billion times over with absolute confidence and guarantees that it will be that sum one equaling whatever the value, whatever the sum is, um, like why would we ever need to do that again? Um,
Yeah.
so with everything that we have like with everything that's already built in about immutability, memoization is like very simple, very straightforward to do. It just simply means like we could create a map where and maps in Haskell are also lazy in their values, so we could say that we have a map um, with a key with the name of that key being sum1, and then some value for that key, and it will always be the same value.
Yep.
And so that it's again very
Yeah,
easy
and
to implement.
you're
Yeah,
right that it was just the REPL.
yeah,
Because this here, for example, like the reason why this one printed out right in the REPL is because like we're not actually like, how do I say this? Like quicksort is being used at like the outer bound, whereas here we're adding x to the sum.
yeah.
So like from the perspective of the REPL, it always has to add this x plus, and so that's why it like this part is not like it's basically recompute has to recompute that. But if we were to do something like the val plus the val, I think, I could just be hallucinating here, but my understanding is that this, no, okay, never mind. We'll have to play with
Well,
it.
I guess that does illustrate this. Well, it does illustrate what you're saying because, um, let's
Oh yeah,
say
it only calls on list once.
right,
Yeah.
yeah. So like we can see that before and after Kyle added the val plus the val and made that change in the function, the output from trace is still the same, right? And so trace is only printing when there's actually some sort of mechanical evaluation there. But even still, even though we have changed the function so that it adds and uses the val again, it doesn't change what we trace. Yes. And it isn't printing the calc both times, just the once, but you are getting that doubled out value in the end, right? Because like let's say, right, so like to illustrate that further, like let's say the sum of our list is 10, right? So it's like I guess that'd be a 3 and a 4 is our list, and that sums to 10. We just calculate it being 10 once, and then we know from if we want to think of it line through line, we know as of line 59 where we say the val equals x plus the sum, in that recursive step, that the val is 10.
Yeah, but not to throw a wrench in it, it's giving us 258.
Well, you did change the you did.
Yeah, but how do we get it? Should be 30, shouldn't it?
Well, so what I'm saying has nothing to do with like actual value. I will say, um,
Yeah.
it's more the execution steps.
Yeah.
I don't know why it's
Anyways, we're going off
currently.
course here. We're gonna I need to actually think about this one. Because memoization and laziness, it's powerful, but um, it's
Well,
one of those things.
yeah, it's no more complicated than that. I think we're just getting confused by the REPL ultimately.
Yeah. Okay.
I think that's probably the end of the lesson, right? Or
Yeah, that's all I have.
okay. Anyone have any questions or?
Got a little off track there, but I think that was a good little discussion.
I'll also say too. I do have. I don't know what the quality of it is, and it's quite some time ago. I did another recursive lesson like a long time ago, where I just basically I don't elaborate too well, but I just do like a ton of examples of different um, recursive functions in Haskell. I think it'd also be, you know, based on that, like I think it'd be good homework to go and just look at like find a get familiar with the prelude. Like look for the prelude module on Google, and try to find a function that is recursive.